So let me see. Yeah. So I hope you can. Oh, but yeah, you can all see me as well, and also the notes.
Yes.
Okay. Then here we go. So, well, I'd like to thank the organizers for inviting me here to speak. Well, although I cannot be in Ann Arbor, which is one of my most favorite cities, and it's especially my great honor to speak at the Paul Sally conference. I have a very good memory of him. I was a Dixon instructor at the University of Chicago in 2009 to 10. So and he was there. So yeah, well, maybe I shouldn't speak too much, but yeah, well, at first he looked quite intimidating. So I was quite shy and, didn't know how to approach him. But then, yeah, he invited me to his office for a chat, and he turned out to be an extremely nice and gentle person. And yeah, so yeah, I miss him so much. And that said, I'll get to my talk. So the title is on G-spin 2n valued automorphic color representations. All this is based on joint work with Arno Krat at University of Amsterdam, and my talk has 3 parts. As you can see, there's a long background section, and followed by a statement of main theorem in some more precise way. And then in the remaining time, I'll sketch the proof. Okay. So here we go. So yeah, I wrote down something so that I can go through the background section rather fast and get to more interesting stuff. So please bear with me. So the first background is the Langlands dual group. So I understand that there are also young people who are not familiar with all the groups I'm going to talk about. So, and it is a representation theory conference. So it's appropriate to begin with, let G be a connected reductive group over field F, that is local or global field. And I assume that the group is split for simplicity. Most of the time, but not all the time, the group will be split. So instead of with the more general L group, I'll just talk about the Langlands dual group over C or QL bar in my talk. So I'll just maybe write it here. And the definition is that the dual root datum of G hat is, by definition, the root datum of G hat is dual to the root datum of G, and that determines G hat. But that's probably too abstract. So more concretely, let me tell you what this is. Well, when G is GLN, G hat is just GLN, the same thing. But already when G is SP2N, you're going to get the orthogonal group SO2N plus 1. When you have GSP2N, that's a variant of SP2N, in that SP2N just the elements are fixing a given symplectic form. GSP2N, this symplectic similitude group, fixes the given symplectic form only up to scalar. So in that case, the group is slightly different, bigger than SP2N, and turns out that the dual group is G-spin 2n plus 1. And SO2n, well, the dual group is the same. For GSO2n, it turns out that the dual group is G-spin 2n. So for my talk, I mean, these are the most relevant, SO2n and GSO2n, and dually, you have these groups. So, I mean, you can, if you're already familiar, you anticipate that why I'm going to see G-spin 2n valued color representations, because I'm going to start from GSO2n automorphic representations. Okay. So yeah, let's do a little bit of exercise with these groups. So this SO2n sits inside of GSO2n, as I said, GSO2n is basically the similitude group. So instead of fixing the given symmetric form, you only fix the symmetric form of the scalar. And then here, if you just do that, then you're going to get GO2n, the similitude version of the orthogonal group, but then GSO2n means the basically connected component of the identity. So it has index 2 inside of GO2n. But yeah, that's just to stay in the connected world. So don't worry too much about that. Basically, the similitude map is to read off the scalar. When you're given an element, then it moves the, changes the given symmetric form by a scalar factor, and that scalar factor, when you read off, you get this map. And the kernel is exactly SO2n if you think about that. And well, what happens if you dualize? Well, basically you flip all the arrows and then you are going to get this exact sequence. And well, I didn't quite define the G-spin groups yet. That's going to be on the next page. But for now, let's just see what happens. By dualizing, you just get some map from G-spin to n to SO to n. That's what I'm going to call projection or PR. And then, well, it turns out that G-spin to n contains a copy of GM in its center. So we'll see this on the next page more concretely in terms of Clifford algebras. But let's move on. Well, the next exact sequence is, well, when you have GSO to n, you take its adjoint group, modeled by its center, then, well, it's PSO to n, which can be also thought of as SO to n modulo its center, SO to n modulo plus minus 1. And the kernel is the central GM. In this case, well, the dual exact sequence, you still have G spin to n, but then PSO to n becomes spin to n. So it's a general fact that an adjoint group becomes a simply connected group when you dualize. So that's going to be spin group. And well, spin group is the derived subgroup of G spin to n, and then this GM is the co-kernel. And that's what I'm going to call n, because basically it comes from the spinor norm construction of the Clifford algebra. Okay, so that's the first background. Are there any questions before I move on to the next page? Okay. Then, well, the second background is, I need to tell you more about the spin groups or G-spin groups, because they appear quite often in my talk. So what is the spin group? Well, the spin group is the simply connected double cover of the orthogonal group SO. So that's basically the what you want to consider. I mean, really, it doesn't depend on whether you have odd orthogonal or even orthogonal group, but because my talk is going to be mainly about the even case, I'll only think about SO to n rather than SO to n plus 1, and then I get SP spin to n. And well, when you think about the Dynkin diagram of type D, you have this sort of shape, and then there's an order 2 automorphism. So it's an outer automorphism. And well, if you make appropriate choices, I mean, you can actually choose theta on spin to n and theta not on SO to n to have order 2, so that, I mean, their square equal the identity map, and you can also make them compatible if you like through the projection map. So we'll fix these choices, and well, to work a little more invariantly, maybe you want to think of SO to n as SO VQ, where V is a 2n dimensional vector space equipped with quadratic form Q, or a symmetric form arising from that, where in characteristic 0. And well, in that case, I mean, such a quadratic space gives rise to Clifford algebra that is basically a universal, kind of universal associative algebra with unity, where V times V equals Q of V. I mean, Q of V is a scalar, so you just somehow impose this rule that V times V should be this scalar Q of V, and then you can construct this algebra out of V and Q. And the G-spin group can be conveniently realized inside of the unit group of CV. Well, it's maybe if you see it for the first time, then it's not easy to think of it concretely, but if you choose basis, for instance, you can really write down concrete formulas. And a G-spin is basically a subgroup of the unit group of the Clifford algebras. And roughly speaking, well, this Clifford algebra has the plus part and minus part, the even or odd part. And well, basically you want to consider element in the even part such that when you conjugate an element of V, which you can view as an element inside of CV, well, base conjugation by X preserves elements of V, elements of CV coming from V. And that property basically gives you G-spin V. And turns out that when you do this, then this conjugation by X coming from the Clifford algebra lies in the orthogonal group, and it's actually a surjection. So that gives you the projection map that we saw in the previous page. So it's a concrete realization of that, and then, well, you can make choices compatible, like theta and theta naught can be made compatible with this projection map, and the kernel turns out to be the GM, the scalars viewed in the Clifford algebra, and then your automorphism is made to act trivially on the scalars. So basically that's what you're going to get, and basically it's just a concrete realization of what we had before on the previous page. Okay. So, well, if that's a little too much detail, maybe you can try to just remember this exact sequence. And then the final thing we want to remember about the spin group, or G-spin, is the following representation. So we have a very nice construction of representation, an algebraic representation of G-spin. To do that, you choose a maximal isotropic subgroup, isotropic space in V that's half-dimensional. So V is 2n-dimensional and W is n-dimensional. It's maximal isotropic. And you take its exterior algebra. So that's going to be 2 to the n-dimensional, but if you take only even or odd part, depending on epsilon is plus or minus, then the dimension is 2 to the n minus 1. And there's a natural way to make the Clifford algebra act. So it's a CV module, but in particular, by restriction, you can make the G-spin act. So, yeah, and turns out to be this is an irreducible representation for either choice of epsilon. And that gives rise to the irreducible half-spin representations. And, well, my notation for that is spin epsilon. So that's going to be spin V, or spin G spin 2n, going to GL 2 to the n minus 1. It turns out that this representation is close to faithful, but not quite faithful. There's an order 2 kernel, which is central. Okay, so are there questions before I go on to the next page?
I'm probably wrong. Is that G-spin to GSO, or is it really G-spin to SO?
It's G-spin to SO. Yeah, SO maps more naturally into GSO, and then dually G-spin naturally maps to SO.
Okay, thanks.
Sure. Yeah. Are there other questions? Okay, then let me go to background 3. And then now I can promise you that this is the last background I'm going to cover. But hopefully you get something out of this. So now I recall the statement of the Langlands correspondence, but not in the precise form, I'll only recall as much as I would actually need in my talk. So let F be a global field. Let me start quite general. And there's a conjecture, Langlands conjecture. Basically, it's the conjecture on the global Langlands correspondence, made more precise by various people, like Clausel, for instance, refined the statement when G is GLN, and then Bazard and G, at least in one direction, from left to right, they gave a pretty precise formulation for arbitrary reductive groups G. So the statement is roughly the following. Well, for every L and every choice of isomorphism between QL bar and C, and the reason you need this is basically that the coefficients of automorphic representations naturally lie in C, the complex field, whereas we are looking at L-adic Galois representations. So you need a way to compare the coefficients, otherwise you can't really say they match. So, and the construction does depend on this choice as well. So for each L and iota, you have a correspondence, and here I have arrows, but I really mean correspondence in this generality because, well, basically it's the multiple things corresponding to multiple things. It's not like one-to-one in general, although for GLN, you can make that happen if you say things precisely enough. So, so yeah, on the one hand, I have automorphic representations. Again, you need to put an adjective, like you need to impose some version of algebraicity, otherwise it will be completely transcendental and there will be no Galois representations corresponding. But let's just say suitable automorphic representations correspond to suitable L-adic Galois representations. And well, how do we characterize, I mean, when can we say that the two things match, pi and rho match? Well, for my talk, I'll only consider the following for almost all places V. The V component of pi, which I call pi V, corresponds to rho V. That is nothing but the restriction of rho to the local Galois group at V. And almost all means, it's kind of the usual terminology, meaning all but finally many, with finally many exceptions. And more precisely here, I mean that both pi V and rho V are unreified. In that case, I want to say that they correspond according to the unreified local Langlands correspondence. Local Langlands correspondence. So maybe later I will just write LLC, and the unreified local Langlands correspondence is not a conjecture, but a theorem. It's relatively easy theorem in this business. So there's no ambiguity in saying this. Although, as I said, I mean, the conjecture is in rough form and you need to worry about various normalizations and etc. But that's basically the form of the conjecture. Okay. Are there questions about the statement? Okay, then, well, a quick quiz or question is which arrow, I mean, there are two arrows here, right? Arrow number 1 and number 2, whether, depending on whether you want to go from automorphic to Galois or from Galois to automorphic. So the arrow 1 is often called construction of automorphic Galois representations coming from the automorphic side. And the second part is often called the automorphy of Galois representations. Given Galois representations, automorphy means whether there is a corresponding automorphic object. And well, you can probably you would have guessed that I'm going to talk about only number 1. Starting from some automorphic representation, how do you construct the corresponding Galois representation? And in general, it's not, as I said before, it's not going to be unique. There are some group theoretic issues, but I'll probably say more about that when I get to that point. And for now, let me tell you some of the known results. There are so many kinds of results. It's almost impossible to give a comprehensive list. But let me just mention that when F is a function, global function field, and G is GLN, it's basically a theorem due to Drinfeld and Laurent-Lafogue. And well, of course, I mean, there are various people contributing to all this. And most recently, when G is an arbitrary reductive group, at least the arrow 1 has been constructed by Vincent-Lafogue, and for which I guess he was awarded the breakthrough prize. And what happens when F is a number field, and when I'll only focus on the case where pi infinity is regular, the Archimedean component of pi is regular, basically means, well, the infinitesimal character is regular, but in fact, I also require that it's algebraic secretly. I didn't write down, but up to suitable normalization, I require that the infinitesimal character is actually algebraic in a suitable sense. But well, when G is GL1, or a little more generally, when G is a torus, this is a well-known theorem. It's just basically a reformulation of cloud field theory. And in fact, the whole Langlands business can be, to a large extent, can be thought of as a non-abelian generalization of cloud field theory. And when G is GLN and F is total real, or CM, well, for GL2 over Q, there's classical work by Eichler, Shimura, and Deligne in 1960s. And then, well, a lot of people have contributed to this, but most recently, the most general case has been obtained independently by Harris, Long, Taylor, Thorne, and Schulte about 5 years ago. So at least when pi infinity is regular and you have this situation, then you have the arrow 1 from left to right. And when G is a classical group, basically, well, I said G will be mostly a split group, so I put a little round bracket around UN, but you can allow UN as well, or also an symplectic group. And then basically the theorem or the conjecture constructing the arrow 1 can be reduced to 2 by applying the functionality lift results by Arthur and other people, either by the trace formula method or by the L functions method, whenever they're applicable. For instance, when these are quasi-split groups, we are okay. And F is as above, so total real, or CM. Except that, I mean, there's a little bit of problem when G is SO to N, because, well, I don't want to get into this for now, but because SO to N has this non-trivial auto-automorphism, you're going to have some ambiguity when you try to prove this. And basically, what you're going to get is that if you just do it this way, then you can say that these two things correspond up to auto-automorphism. They don't just correspond under local Langlands, but up to auto-automorphism ambiguity. So even when SO to N, you don't really get the conjecture just from the known results. Okay, other questions? All right, then let's see what is the goal of this talk. Well, I can say that
Can I ask a question?
Yeah, sure.
Could you explain more what you mean that even, I mean, about SO2N?
About,
I mean, you expect the local Langlands for SO2N, right?
right, your SO2N case, you're saying.
Yeah, but I
Yes.
mean, what's the, I mean, I understand the auto-automorphism stuff, but What was the impediment to getting anything about it, which is?
So the problem is that, I mean, this construction a priori is, so what do you do? Well, if I have time, I'll get to this, but you start from SO to N and then automorphic representation. You go to the GL to N automorphic representation, that is self-dual. You apply this construction to get a basically self-dual Galois representation into GL to N, which factor through SO to N. But basically the problem is that you only know that these two things correspond after applying the standard representation. Yeah, but then when you have like two SO to N conjugate classes that become conjugate in GL to N, that only tell you that they are in the same outer automorphism orbit.
Okay, good.
So yeah, that's the problem, and there's no. It seems to me that there's no easy way to resolve this, and also this ambiguity is carried basically everywhere in Arthur's work as well, so far as I can see. Okay. All right. So the goal is, yeah, basically to prove the conjecture, and at least concerning the arrow 1. So that is, I start from GSO to an automorphic representation. I obtain some Galois representation. Gamma F is the full Galois group over F, and then into the dual group of GSO to N, which is G spin to N. Well, such that, well, basically I have this correspondence, unreified Langlands correspondence at almost all V. And well, that would be very nice, but unfortunately for now, due to some technical difficulty, I'm assuming some local hypothesis on pi. And I'll get to this, and I'll tell you what I'm assuming and why I'm assuming them. But I'll also say that something similar was done when the group is GSP to N over total real field. Also, in this talk, I mean, this GSO to N over F, that is total real. And that's also with Arno Krat, and the work has been around for some years, so you can check that out. But turns out that the GSO to N case is more difficult than GSP to N, partly due to the presence of outer automorphism, and also if we have this half spin representation rather than just a single spin representation, so there's some difference depending on the parity. Basically, this case is somewhat more difficult. And well, before I get to the more precise version of the statement or theorem, I'll just look at the group theoretic aspect. Eventually I'll mention something about Shimura varieties a little bit, but not much. I'll just concentrate on the representation theoretic aspect. So when I look at the group G spin to N, we've seen 3 representations, spin plus and spin minus, and well, actually 4. This projection, which gives rise to, if you like, by embedding in GL to N, I have the standard representation. So maybe I'll call this, I mean, this is maybe standard. And well, what I want to say is that in reality, I mean, it would be nice if there is a magical way to construct this map directly, but I don't know of such a technique. And most techniques we have construct Galois representations into general linear groups only, at least a priori. So when you look at this picture, then what you really hope to get from, say, geometry or by some other way is usually these representations. Actually, you should try to have 2 for spin plus and spin minus, and then maybe this. So this rho pi, you can't really construct directly, but you can hope to construct rho pi composed with some representation of G spin 2n. These we can try to construct. So rho flat. It turns out that the map into GL1 is not quite necessary, that's superfluous, but turns out that this thing is relatively easy to do. I mean, at least if you try to deduce, you can deduce this from existing theorems with some work, but not too much. You need to work some more to get this, and I'll tell you that they eventually come from Shimura varieties of certain type. But then there's a problem of group theoretic problem of putting them together to really construct rho pi. That turns out to be also non-trivial. So I'll try to explain all this. And part of the underlying difficulty is that G-spin has some group theoretic features that make it a bit more difficult than some other groups, like general linear groups or classical groups. So I'll get to that. And yeah, well, passing on, this will become relevant later, but smallest faithful representation of G-spin 2n. I mean, one feature of G-spin 2n is that you cannot embed it in something small. Like SO2n embeds in GL2n, so these groups are in some sense of similar size, but G-spin 2n only embed in GL2 to the n. So faithful representation is pretty large. So yeah, that's 2 to the n dimensional. So that's also like part of the difficulty, that you can't easily construct this inside of some small thing and try to apply some invariant theory. So for those who are familiar with Vincent-Lafolk's work, I mean, there's this general machinery of pseudo characters that work pretty well in that setup, but somehow in the number field case, we don't have like corresponding geometric objects to hope to construct similar things. So the same technique doesn't seem to work, at least with the current technology. So we need to come up with a different way to construct this representation. There are questions? Okay, so let me try to make things now more precise. That was, as I said, that long background section. By the way, when am I supposed to stop? How many minutes?
It's 15 minutes. So
15?
No, 5. Yeah, you started at the talk is 15 minutes. Yeah, total.
Okay, so that's
so about a little more than 15 minutes. We can take a couple minutes extra because of Stephen's jokes.
Okay, then yeah, I'll think of that as like about 17 or something. Okay. All right, so the main theorem, well, so there's some parity condition involved in my talk. So that has to do with the group over R, we're at real places having discrete series representations. That's kind of relevant to my talk, but maybe I'll just say something quickly and then get to our actual setup. So also, if you think of the real forms of the orthogonal group SO2n, then, well, and when you think about which ones have compact maximal torus, then when n is even, then you can consider the split SO(n), n, but when n is odd, SO(n), n doesn't have discrete series, but you should look at SO(n plus 1, n minus 1, that is quasi-split but not split. So there are two outer forms here. And Harris-Chandra basically tell you that you need to have this compact torus in the derived subgroup to have square integral representations, or aka discrete series. So our setup, basically because the method relies on partly on Shimura varieties and taking cohomology of Shimura varieties. In particular, we want G to have discrete series at infinity. And when we are working over to a real field, basically at every infinite place, we want to have this. So that basically make us consider the following group. When n is even, we can just take the split form as GSO to n. But when n is odd, we really need to take some outer form. So this is quasi-split, but not split, relative to some CM quadratic extension over F. But don't worry about it, because I'm going to just concentrate on this case, which is a bit simpler. The other case is actually one more layer of difficulty, but let me not worry about that. So quietly, I'll assume n is even and we are dealing with the split group only. In this case, well, the assumption will be that, well, at one point I have Steinberg component, so Steinberg up to character twist for some finite prime q, and then
So
we have this. Yeah.
Can I? There is a question in the chat. Can I?
Sure. Yeah. Sure. Please.
So it's from David Wogan, and his comment is there are no Shimura varieties for the split form, just for something inner to split.
So for no Shimura variety for split, sorry. Could you say again, the no Shimura variety?
There are no Shimura varieties for the split form, just for
the
something.
split form. Well, yeah, if we need to take GSO, I'm not sure about if you just take SO to N. When we have G, I don't think there's a Shimura variety for split SO to N, because well, I have to think about it more carefully. But in this case, yeah, it's really it's important that we have the dual group has the spin representation. It turns out, I mean, there's some kind of classification of Hermitian symmetric domains, and yeah. So in other words, maybe you have something for PSO to N, but I don't think we have something for SO to N. But yeah, I need time to.
Yeah. Thank you.
But it has nothing to do with the splitness. It has to do with the orthogonality, right? I wonder if David.
Is that right? Yeah, I mean, I'm happy to discuss further. Yeah, I mean, basically, there's a pretty clean classification by Delin in his Corvallis article on Shimura varieties. So,
but they don't exist for the split versions, only for.
I see what you mean. Sorry, yeah, sure. I mean, the Shimura varieties. For Shimura variety, I need to take it takes a suitable inner form of this split group. But yeah, depending on the parity of n, sorry, I totally misinterpreted your question. We are not associating Shimura variety directly with G, but with the inner form of G over the real, we are going to take compact forms at all but one real place. At that real place, we are going to have this SO star to N type, the kind of quaternionic stuff. Yeah, so yeah, we are not going to use split SO to N. And in that case, yeah, when there's a Shimura variety for SO n-2,2, and there's also SO star to N. That's a different thing. And yeah, we are going to look at SO star to N. I hope I answered your question this time.
Thank you. Yes.
Sorry. Yeah, I was focused on this the group I'm starting with, but yeah, it's by some transfer to inner form. I need to go to an inner form and then apply this streamer override construction, which I was planning to sweep under the rug. But yes, thank you for pointing that out. Yeah, so the second condition is L cohomological. That's what this means, but it really means for me, under suitable normalization, this basically is equivalent to pi infinity is square integrable. In other words, at all real places, you have square integrable components. And then standard regular basically means pi infinity transfers to regular representation of GL2N under the standard representation of the dual group. So I explained the spin to N map to GL2N through SO2N. And when you transfer, I mean, you can just transfer the parameter or just, you can phrase this in a few different ways in terms of the L parameters or just infinitesimal characters. But yeah, it's a pretty mild condition for G spin to N, but it is a non-vacuous condition. On the other hand, I think I can really remove this by working a bit more, but for now we keep this condition for a technical reason, and I'll hope I have time to explain why. Okay, so
you're welcome to take a little bit longer if you need.
Yeah, well, yeah, we'll see. I hope not to go over too much, so I'll try to keep in reasonable length. So right, so I introduced these three conditions. So the main theorem is, well, first of all, there's the odd case where I should consider quasi-split form, but let's say N is even so that I work with the split group. And then I have this automorphic representation satisfying these three conditions. Then, of course, the statement should be that there exists rho pi corresponding Galois representation, the elliptic Galois representation. But thanks to my running assumptions, actually, it turns out that up to isomorphism or up to G spin to N conjugacy, there's a unique Galois representation such that, I mean, well, these things correspond at almost all V. So that's going to be the main theorem. And let me give some quick remarks. So this basically gives a, well, implies a similar theorem for SO2N as well. I mean, it's kind of interesting, but as far as your SO2N representation extends to GSO2N representation, which is basically a condition on its central character, yeah, you can, I mean, so such that this hypothesis hold, then, yeah, you basically by going through the GSO2N construction, you can improve on this SO2N. Namely, I mentioned some outer automorphism ambiguity, but that can be removed by working through GSO2N, so that you really have this correspondence in the in the SO2N case, you have this correspondence on the nodes, not up to outer automorphism. That's a nice application, I think. And then there's also, in these circumstances, it shouldn't surprise automorphic experts, but basically having Steinberg component, and yeah, that basically, and we actually use other conditions as well, but we can prove that the automorphic multiplicity is 1. And also there's we have this meromorphic continuation of L S pi spin plus and minus. So we have this half spin L functions of pi, and our theorem actually gives enough input about this scalar repetition such that we can apply the potential automorphic theorem by Barnett, G. Garrity Taylor, and also by Patrikis Taylor. So the point is that we know enough about these scalar repetitions so that the potential automorphic theorems apply to tell us there's a metamorphic continuation. So that's pretty much the second part of my talk, and in the remaining, I don't know, maybe 5-6 minutes, I'll tell you something about the proof. Before that, other questions? Okay. So, so we have this situation I told you before. So G-spin has these interesting representations, and then we want to basically construct these solid arrows. But in fact, well, I don't really need this 3, but I'll say maybe rho plus and rho minus, and maybe I'll say rho flat. So rho plus, rho minus, and rho flat. And what I mean is, for instance, rho flat, I want rho flat to be, this should be this projection composed with rho pi. And what that really means is, well, we don't have rho pi yet. So what do we mean by having this? Well, basically the locally rho flat at V, localized at V, is basically, well, not rho pi, but rho pi should be what? Well, at V, it should be basically the local line length parameter for pi V. As far as pi V is unramified, you can make sense of this L parameter, unramified L parameter. And this unramified L parameter, that should be basically the V part of rho pi, and then that's compatible with this rho flat. And similarly for rho plus and rho minus, so rho epsilon is basically the spin epsilon, and then, so that's what we want. At least locally, we get the correct representations, rho plus and rho minus and rho flat, and we'll worry about gluing them together to somehow obtain rho pi. And I think I may not have the time to tell you about the gluing part, but let me tell you what happens to these constructions. So for rho epsilon, I mean, the basic idea is to realize in the cohomology of the Shimura variety, attach it to restriction scalars from F to Q. F is the total real base field. And as David asked, well, I don't take G itself, but G natural, because it's a more natural inner form to which I attach a Shimura variety. So it's an inner form G over F and X epsilon. So there are actually two choices of the Hermitian symmetric domain X epsilon matching this group. And we realize in the cohomology of elliptic cohomology of this Shimura variety, this scalar representation. And I mean, when you go through all this, you realize that this assertion that we want, I mean, that basically there you can take the pi part of, I mean, in the cohomology of realizing the elliptic cohomology of, well, pi part, I would say. So pi part of elliptic cohomology of this Shimura variety, and that gives you a good candidate. But then why is this the right thing? Why do you get rho epsilon with this correct property? For that, you have to go through some general thing. general argument envisioned by Langlands and Rappaport and Kottwitz. So, so Langlands-Kottwitz method so tells you this star. So this is star. Okay, so this is based on recent work by Kissin on Langlands-Rappaport conjecture and the forthcoming work by Kissin, Zhu, and myself. And then the second part, rho flat, that is the at least easier in the sense that we don't have to do that much extra work. But here's the basic idea I tried to explain in response to a question before briefly, but there's an SO to N representation, well, maybe GSO to N representation pi. That's where I start from. And then by restriction, restricting from GSO to N adelic to SO to N adelic, I just pick some irreducible subrepresentation called rho flat. And then by Arthur's transfer, I can transfer to GL to N, which is actually self-dual. And there's a well-known construction to give you a Galois representation into GL to N. So this really goes from gamma F to GL to N, but then this factor through SO to N. And self-duality by itself is not sufficient because you need to tell whether it's symplectic or orthogonal, but this factor through SO to N, there you use some work by Belash and Chenebier that they tell you that this should factor through SO to N. So that's how you get this rho flat Galois representation into SO to N. And then now, yeah, well, there are some remaining things, so I should really stop. So yeah, there is some caveat because this general gluing procedure doesn't work without this hypothesis. That's where you need to use this Steinberg hypothesis is used. So I should say that. And then here, if you really think about this step, that step doesn't work without assuming the standard regular hypothesis. So that's why I need two assumptions. But well, other than that, let me stop here and I'm happy to answer further questions. Thank you so much.
Thank you, Sugu.
So yeah, for people who are interested, I'll just turn to the next page. And actually there's one more page, but I don't mind. I mean, this, yeah, it does take a little more time to explain the gluing part.
So in fact, I would, if there are any questions, we can take it now a little bit, but I would like to remind everyone that we have a half-hour break, and if you have further questions, Subbu will be available in this room to discuss some of these topics further.
I wanted to ask if you have this rho minus and rho plus and rho b, is rho pi unique? Can you have different? Mm-hmm.
Oh, sorry, just abstractly, you mean?
Abstractly. Mm-hmm.
I don't think so, because yeah, what I wanted to say is that there's a notion of acceptable group by Michael Larson, and then by his classification or by his results, the G-spin group is unacceptable, which means that basically something funny can happen even if you know rho plus and rho minus, I mean, up to isomorphism, or actually even if you give yourself spin rho pi composed with all irreducible representations of G spin to N, let's say, that's still insufficient to pin down rho pi up to conjugacy.
So you construct one rho pi which satisfies these conditions.
Yeah, but then because of, thanks to my running assumption, in general, there's this group theory difficulty, but under my assumption, I can say that rho pi is actually unique optoconjugacy, so unique optoisomer.
Under the assumption.
And if I have to say one word, then what makes it possible is this hypothesis. Morally, I mean, this hypothesis is doing the job, because eventually this tells you that the image of rho pi contains a regular unipotent element, and that's a pretty strong condition. Because rho pi is also semi-simple repetition in the sense that the Zariski closure of the image is going to be a semi-simple group, possibly disconnected, but semi-simple group. But yeah, to be a semi-simple, reductive group, sorry. A reductive subgroup which contains a regular unipotent element of the ambient group cannot be completely arbitrary, and yes, rather well behaved. And we do use some classification theorem there on reductive subgroups.
Thank you.
Any other questions?
Can you say a little bit more about the Langlands-Kottwitz method that you used?
Oh yes, it's something I decided to suppress almost completely. But yeah, at least I should probably have said that this Shimura variety is of abelian type. Otherwise, we don't know really what to do. And yeah, in this case, it's basically Kissen proved the Langlands-Rappaport conjecture, but that basically describes the points of the Shimura variety modulo good reduction prime P and with various actions, Heck and the Frobenius action. But by itself, it doesn't quite tell you what the scalar repetition should be. And for that, you need to go through the Langlands-Kottwitz method. So what's the next step is, starting from this construction, you need to apply the fixed point formula, Lefschetz fixed point formula, and then basically you can express the Frobenius trace in terms of some horrible trace formula, in terms of terrible linear combination of orbital integrals. But then, yeah, you need to go through some stable trace formula business to figure out what this is really telling you. So yeah, there is some complicated procedure which is simplified. And this is another time we use the hypothesis ST. When you have a Steinberg component at a finite place, the trace formula simplifies tremendously. So we don't need to worry too much about endoscopy here, which is one of the biggest headaches in this business.
So if I understand correctly, so what is new that's not in Kissen's original paper? Because you wrote there are two papers, right? What's new in this later paper is using the stable trace formula?
Yeah, so Kissen describes
he did the multi points decomposition,
yeah,
right?
Yeah, Shimura variety, FP bar points of the Shimura variety with Frobenius and Heck action. But if you think about what you really want, then you want to somehow, after applying fixed point formula, you need to turn this into an expression in terms of automorphic representations. But of course, I mean, a priori, yeah, this description doesn't quite know about that.
Right.
When you apply the fixed point formula, you just get a bunch of orbital integrals, and they don't look the same as the orbital integrals appearing in the Arthur's trace formula. So you need to massage this quite a bit to really compare with Arthur's stable trace formula. And eventually you get some sort of automorphic description of the cohomology Shimura variety with Frobenius action. But yeah, there's some complicated procedure. And but then actually, I would say actually that's the usual story of Langlands-Kottwitz, but the additional layer, I mean, what's really one of the main points here is that Kissen's proof of Langlands-Rappaport conjecture proves a weaker version, actually. And this fact causes a lot of trouble, a lot of technical trouble. So it's not quite the original Langlands-Rapoport conjecture in its full strength, but something weaker. And then, yeah, there's some ambiguity floating around, and yeah, you need to really work hard to deal with that.
Could you say a few more words about what exactly, like how exactly is Kissen's result weaker than this later your joint work was?
Before that, we need to just make a quick announcement for people who want to go to GatherTown, how to do that, and then we can continue with the questions. I think Jessica was going to speak to that.
Yes, but I mean, let's first thank Sogre again.
Yeah, let's thank the speaker first.
For having me.
Thank you. And as Lauren pointed out,